This is good. So in section 2.3, we get another method for solving DEs, but it's special. It's called, well, here it is. It's called the integrating factor method. Integrating factor, bless you. Integrating factor method. It is a method for solving, it's good for first order linear DEs. So that's what it's good for. Remember that separation of variables that we were doing, it was good for maybe linear or nonlinear. Also first order, though, we're doing first order only, bless you. But for the linear ones, I don't know, there's this special method, the integrating factor method. Now, hang on, if you do have a first order linear DE, let's see, in general, it kind of, yesterday I wrote down this nth order linear DE. Let me just write a general first order linear DE. I guess it would look like this. I mean, right, there's got to be a y prime, there might be a y, there might be a coefficient functions of x, and it might equal some g of x. I mean, that's kind of just a generalized linear first order DE. But to do this integrating factor method, if we start with something in this form, anyway, we want it in this, start in this standard form. And standard form doesn't want this coefficient here. It wants this to be a 1. So whatever's here, if you start with one of these and you got some coefficients here, even just a 2 or an x or whatever it is here, you need to get rid of it. So you need to divide by it. So I'm going to divide by this coefficient. And then watch this. I'm going to rename all this stuff now. Watch. So once I divide by that coefficient, this is dy dx with a coefficient of 1. Okay, now I'm going to call this is just some crap divided by some other crap. But now I'm going to refer to it as p of x times y. And then this other side, it was some g of x and it was divided by some other x's, and now I'm going to call it f of x, if you don't mind. But now you're in standard form for this method. And then the first thing you do is, once you're in standard form, maybe the first thing you do is put it in standard form. Then the second thing you do is you find the integrating factor. So you find the integrating factor. And the integrating factor is this funny thing. Check it out. The integrating factor is this. E raised to the integral of that p of x dx. It's e raised to the integral of that term right there. That's the integrating factor. It's wild. E raised to the integral of this p of x thing. And then you find it, and then you do stuff with it. Listen, to finish this problem, let's do a real problem. But this was the theory to get us started here. So let's do a real problem. So I'm making up a real problem. How about that? A real problem here. All right. All right, hey, look at this. There we go. That's a nice, that's a differential equation. It's first order. I believe it's linear.
It's not in standard form.
It's not in standard form. We need, if we're going to do our integrating factor method, we need it in standard form. How do I put it in standard form?
Divide everything by x.
Divide by that x, right. Divide by that x. Okay, we'll do that first then. We'll divide by x, we'll divide by x, we'll divide by x. And so now we've got it in standard form. Now it's in standard form. And so then the first thing we do is, and by the way, I'm going to run through an example of this method. And then I think I'll kind of write down the steps for you, but I'll do this, we'll talk it through here one time first. and then I'll give you some good notes on what the steps were that we did. But the first step was put it in standard form. Now the second step is find this integrating factor. Now here it is. It's this trick. The integrating factor is e to the integral of that -2 over x. So you got to go off to the side and find this guy. And find this and clean it up. So what is the little integral of -2 over x? -2 ln x. Do you guys agree?
Yep.
By the way, when you do this little baby integral here, you don't put a plus c. We don't need to put a plus c here. But
would that equal 1 over x squared?
well, hold on. You're on to something. Thank you. Let's clean this up. These do clean up sometimes. Sometimes they don't. But with that log and that e, you're suspicious that we could cancel that. We can cancel that, but we got to move this -2 out of the way here. So that's a property of logs that says you can move that up as an exponent. So then you have e to the log x to the -2. Now the e and the log do cancel, and here's my integrating factor, x to the -2, or 1 over x squared. But that's the integrating factor in its simplified form, right? You should simplify it as much as you can. All right, cool. We found the integrating factor. I'm going to call it the integrating factor. Okay, the integrating factor. I'm not even sure why it's called that. Anyway, the integrating factor. Now, what do I do with it? I haven't told you this yet. Here's what I do with it. You go back to your DE and you multiply the whole damn thing by your integrating factor. And by the way, I'll write these notes down in a minute, but I multiply everything by this x to the -2. X to the -2 times y prime. X to the -2 times this. Watch for your signs there. Yeah, that's cool. And then x to the -2 times this. You guys okay? That's what you do. You multiply it through. Now, let's actually do a little work. Well, I can't do much work here. This is x to the -2 times y prime. Here, let me just leave that alone. What can I do here? I can call this -2 over x cubed. Maybe, right, you guys? Simplify this, or I could call that x to the -3 times y. Over on the other side, what's this? 5 over x. Thank you. Okay, here's what always happens, and again, I'll give you some good notes in a minute, but here's what always happens. After you multiply through by the integrating factor, the left-hand side becomes the derivative of the product of the integrating factor times y. Did you hear that? It's just automatic. What you force this left-hand side into is you force this left-hand side into being this. So I'm not, from here to here, I'm recognizing that the left-hand side is this. It's the derivative of the product of the integrating factor times y. So I just didn't do too much. From this step to this step, I just recognized that the left-hand side is the derivative of the product of the integrating factor times y. Now let's just check it out. Look, if you were to do this product rule, let's just check it out. If I was to do this derivative product rule thing here, what would you do? Write down the first, take the derivative of the y prime, plus take the derivative of this guy, which would be -2 x to the -3 times the y. And it's cool. It always happens like that. When you find the integrating factor and you multiply through by that, and you're forcing the left-hand side into this every time. You can almost get kind of robotic about it, but be careful. You should maybe do the steps. But it's turning into this every time. So hopefully you believed all that. Now, hang on. Next step. We're trying to solve for y. Remember, we're solving a DE. We're trying to solve for y. We're not far from getting y. If this is the derivative of a product, if I want to kill the derivative symbol, maybe I should integrate. I integrate both sides right now. Moving over here. Integrating that derivative, though, is just canceling that derivative. So I'm left with x to the -2 times y equals the integral of this other side, please. The integral of this other side. That's easy. What is that? 5 ln x plus c. That plus c is very important right here. And look, dude, you're one step from finding y. How do I get y? Somebody might say divide by x to the negative 2. But another way of saying that is
Multiply x squared.
multiply by x squared. Yeah, thank you. I'd rather do that. Multiply by x squared, we'll cancel that. Multiplying by x squared gives me this. And multiplying by x squared times the c gives me this. I'm finished. We found it. We got ourselves an explicit general solution. We're done. If I had an initial condition, I could find c, but I won't. That was cool. That was the integrating factor method. That was just one example.
So we took our integrated factor and multiplied it by each term, and
Yes.
then then integrated both sides.
Kind
and
of.
from there we solved for y.
Kind of. Kind of, yes. Yep. Let's just recall those steps. You're right. I mean, I'm going to write it down like steps now. That's why I told you I promised you this. Let me just do this. So when you do this method, step 1 is, can I say put it in standard form? Can I say that? You know what that means. Put it in standard form. So you saw that's what we did first. We divided by that x. So then once we're in standard form, sometimes they start in standard form. Anyway, now that you're in standard form, what's the next step? We actually go find the integrating factor. Just go find it and simplify it as much as you can. Find the integrating factor. Okay. After you find it, do you remember what we did?
We plugged it back into, we took the integrating factor and multiplied it through.
Yeah, I'm going to say that. So we multiply it through the entire dE, through the differential equation. Is that okay with you? Multiply it through the dE. Yes, sir?
If it always comes out to the derivative of the integrating factor times y, why don't we just use that if we're going to simply integrate in the end?
Well, you know, a teacher does one problem and explains things to students, and then students look for shortcuts right away. So that's what you're doing, right? Is that what you're doing? You want to write less? You want to write a little less? Are you concerned about the amount of lead in the world, or what's your problem?
I'm just wondering.
I'm kidding. Yeah, you're right. Yes. Again, when you do math, you see patterns and you see shortcuts, and you just yes. You multiply through it, then you multiply it through. Then what do? After you multiply it through,
For y.
See, after we multiply it through, here was the cool step. After we multiply it through, and this is the step he's talking about. After we multiply it through, the next step is kind of not to do anything except to kind of rewrite the left-hand side. The left-hand side is the product rule derivative product of, and so here's how I'm going to write that. Recognize, after you multiply it through, recognize the left-hand side, that's what that says, left-hand side, is the derivative of the product of the integrating factor times y. That's what it always is. It always, yes, the integrating factor times y, or the function. Hold on. Recognize that the left-hand side is the derivative of the product of the integrating factor times y. Not only should you recognize it, but then you should write it as such. Write it as such. I love talking like that. I feel like a judge or something. Makes sense though, doesn't it? That is that next step. The next step is kind of a funny step. Recognize that the left-hand side is the product rule derivative of, is the derivative of the product of the integrating factor times y, and boom, write it as such. What's the next step?
then solve for y.
Well, almost, hang on. So after we wrote it as such, there was one, so then we had this. We wrote it as this derivative, then what did we do?
We integrated both.
Then we integrate both sides. Okay, I'm down here at the bottom, but that's cool. Integrate both sides, right. That is the next step. Integrate both sides. Hey, and after you integrate both sides, you've exposed this y, then you're here, and you kind of got one more move.
Solve for y.
Solve for y. Yeah, solve for y. Okay, good. Anyway, and Zachary's on to something here, because there's this guaranteed thing that's always going to happen. You can sort of figure out a way to take some shortcuts, perhaps. I've been teaching this a long time, and I know what happens. Sometimes with shortcuts, you kind of forget things, though. You might, if you shortcut your way into something, you might forget this step. You might forget the multiply through step, you know, because once you find the integrating factor, you do multiply through. After you multiply through, you just recognize that it's actually this. So you could sort of skip to this. Except, what did you do in there? You did multiply through by it. So you got to make sure your right-hand side gets multiplied through by the integrating factor. Anyway, just be careful, do the steps. But, yeah. Yes, sir?
No, actually, your method's better. If you had said in the first place, yeah, that's fine, I would have gone through I would have just ended up setting that derivative always equal to the right-hand side before multiplying.
So you would have screwed up.
Yep.
I know. Sometimes teachers are wise, I know. Well, we have cautions that we worry about because we've seen things. Yeah, okay, anyway, cool. I'm glad you can see that. You can see my point. Right. All right, we should do some more. You know, one of the little glitches that gets people, and I just did this problem, and I did it kind of fast, but a terrible mistake, and to me it's terrible because it really ruins the problem at the beginning, is at the beginning of this, somebody will look at this and say, oh, I got to go find the integrating factor. So it's e to the integral of the 2 over x. Watch, they'll do this. They'll put the 2 over x. They'll focus on the 2 over x. They won't realize, or they'll forget that the sign comes with the term. And then that really kind of ruins the problem, because now it's an x squared, and it really changes everything, and the whole problem's really wrong. So the sign comes with the coefficient. If there's a negative sign there, it's part of what we're integrating here. Right. I mean, it's just a common mistake I see, so I'm calling it to your attention. Yeah, let's try another one. What if we try one like this? Yeah, okay, this one might be tough. I mean, not really. It's not too tough, but it's gonna happen. It's good because it brings up things we need to remind ourselves of. Some things, you know. One big tool we're doing in this class is we are integrating, and so we need to remind ourselves how to integrate some stuff occasionally. This is going to be a good one, I think. Hey, you know, I'm starting at the beginning here. It's already in standard form. Do you guys agree? So all I got to do is find the integrating factor. I think this time it's a little easier integrating factor rather than all these steps. Watch, here it is. It's e to the integral of a 5. So what is the integral of a 5? 5x. So I guess my integrating factor is e to the 5x. Again, don't get too crazy. This one involved logs. Because it involved logs, we could make some moves and do some simplifying. This one doesn't, so we're done. That's my integrating factor. Okay, that's my integrating factor. So what do I do with it? I multiply through by it. Now I'll write that out. You multiply through by it. You multiply through by it. You multiply through by it. So what I just did, I multiplied through by it. The next step's a little funny. The next step just says you don't really do anything except you recognize that that is, and which you don't even have to recognize because it's guaranteed to be the derivative of the product of the integrating factor times y. So you write it as such. So you write it as the derivative of the product of the integrating factor times y. The derivative of the product of the integrating factor times y. You got to run through it a few times to get the hang of it, but it's not that bad, but you multiply through by it, then you kind of alter the way you write that other side. So some people might say, let's just skip to this side, right? I mean, let's just skip. When I multiply through by it, I know the next step is this, so I can skip to this. That's totally cool, but you got to remember to multiply it on this other side, right? Yeah. Now I integrate. So, and you know, again, on the left-hand side, integrating is no big deal because you're integrating a derivative. So integrating a derivative, you just get e to the 5x times y. On the other side, when you integrate, you got to figure out how to integrate. Good. In Calculus 2, in Chapter 8, you had some integration techniques, and one of them is integration by parts. I would do integration by parts. So, hang on. I'm gonna give myself some space. I'm gonna go over here where I got a little room, and I'm gonna do integration by parts. I'm gonna remind you of this here because I feel like, you know, I'm integrating this thing now, and I'm gonna do integration by parts. You know, integration by parts was kind of a pain. You would let u equal something, you would let dv equal something, you would then find du, and then you would find v, and then you'd go for the pattern. The pattern would be the integral, what the hell, u dv equals uv minus the integral of v du. So you would do this formula now. But for certain integration by parts problems, there's a shortcut called the tabular method. Have you heard of that? Yeah, that's sweet. And that's what this is. And that's what so I don't mind an integration by parts problem if I can do a quick tabular method. It's not that bad. So let me remind you of that. So rather than doing the full-blown integration by parts, because I can do a tabular method, I can do, it's a shortcut of this. And the shortcut for this is called the tabular method, and it would be, you kind of make a table, and you put u here, which is going to be the x squared, and you take the derivative until you get to 0. So that's 2x, 2, and 0. And then what do you do here? You put your dv here, which is e to the 5x, and you got to do little baby integrals here. So when you're integrating an e to the 5x, you're doing little integrals here. So you get a 1/5 e to the 5x. Do you guys agree with that? Right here, you're integrating. And you do a little u substitution, and it spits out a 1/5. It's not a chain rule. It's an integration, and it's a little u substitution, and it spits out a 1/5. You integrate again. It spits out another 1/5. I guess you do it one more time here. It spits out another 1/5. Over here, you put plus. You start with a plus sign, a minus sign, a plus sign, a minus sign. And then the answer is staring right at you. It's this initial u, but it's this initial v. It's this initial uv. So there's your first uv. So you have to drop down a level. And it's this term plus this term plus this term. And we're done. I'm going to go write that answer over here. It is 1/5 x squared e to the 5x negative 2/25 x e to the 5x, and then positive 2/125 e to the 5x. How you guys doing? You with me on this? You remember how to do all this? Good. Anything I left out in this answer? Tell me what I left out.
Plus C.
Thank you. You need that damn plus C. You need it so bad. Because what you're about to do, because it's not just a plus c. Well, you'll see. What's it about to be? You're about to divide by e to the 5x. So y equals, and when you divide by e to the 5x, it's going to cancel there, cancel there, cancel there, but it shows up here, you know, so that c is important. You end up with this c over e to the 5x. But anyway, it cancels here, it's canceling here. I get 1/5 x squared, negative 2/25 x, plus 2 125ths, and finally a plus c, and I could put over e to the 5x, or I can write times e to the negative 5x. Right, you guys? It's over e to the 5x. I'm dividing by e to the 5x. But right there at the end, I can. That's my answer. We solved the DE. We solved that DE. It's the integrating factor method. And I had to do a little integration by parts here. I did the shortcut tabular method. Any questions anywhere?
When would it be that we can use the tabular method?
Notice you gotta do multiple integration by parts, right?
Well, that's what this would have been. This would have been multiple integration by parts. That's why, right, you do one integration by parts and you end up with, every time you do integration by parts, you bust it into these parts, you perform these little operations, and you end up with another integral to do. And then that integral would have been integration by parts, and you would have done him by integration by parts, and you would have ended up with another integral to do. I think it would have been okay. But then, and you would have had this long answer. So the tabular method is so sweet, isn't it? And you can avoid that integration by parts over. I mean, it's just, it is integration by parts. It's just a shortcut. It's putting it into a table form. And here's the deal. What I learned when I learned this is you can do this tabular method, but you can only do it when you have x to a power times e to something. Because it just works good with x to a power, because the x to a power dwindles down to 0, and then the e function is so easy to integrate, you know, so it works great when you have that. It also works great when you have x to a power and a sine function, because it's also very easy to integrate sine. You get cosine or negative cosine, and you get sine. I mean, it's easy to integrate sines and cosines. So it also works great with a cosine function. But what I learned is that's it. When I learned about this tabular method, the notes and the book said, this is what it works good for. It works good for these three guys. So the good old integration by parts still is useful for other guys that don't follow these patterns. So there is some other times where you may need the full-blown integration by parts, I suppose. Yes, sir.
Say it was, instead of e to the 5x, say it was x squared ln 5x. Would you not recommend the tabular method for that?
See, I don't know. I mean, according to what I read about the tabular method, they don't recommend it. So I don't think I do either. Now let's, in fact, no, I don't. In fact, yeah, hang on a second. So that's a good question. He just said he changed this to an ln. Yeah, I don't think it works. Let's just play with it a second. So what if hang on, because what if I put an ln in here? If I put an ln 5x in here, so what's the derivative of that? 1 over 5x times 5. Or really just 1 over x then, huh? What's the, oh no, I just did a derivative. Oh yeah, hold on, that's the confusing thing, yeah. I'm doing a little integral right here. God dang it, I can't integrate an ln very well. In fact, you know how I have to integrate ln? Integration by parts. Yeah, see, whatever you put in the dv column, you are integrating, which I screwed up there for a second. So, and if you're in it, that's why these dudes are nice, because they're so nice to integrate real easy. Like a tangent over here that's no fun to try to integrate. Or anyway, so no, I wouldn't do. And in fact, anytime you're trying to integrate something with an ln, not anytime, but what often happens with an ln is you do integration by parts, you can't really do the tabular method. You do regular integration by parts, and you let u equal the ln, and you let dv equal the algebraic x squared. And that's kind of counterintuitive. Usually you're letting u equal x squared, and you kill it. But because watch what happens. What happens when you integrate a dv? You integrate to get v, you get 1/3 x cubed. I mean, this seems counterintuitive, like you're growing more x's, you know? But what's the derivative here? 1/5x times the 5. Here I go. I don't know why we got stuck doing this problem now, but that's okay. But this is real live integration by parts, not the tabular method. And watch how beautiful it works. Watch, here I go. The answer is uv, according to the formula up there. The answer is uv, which is this, uv, minus the integral of v du. By the way, these 5's cancel. So v du is pretty sweet, you guys. It's a 1/3 x cubed multiplied by a 1/x dx. This is not bad at all. Basically, it's just an x squared, ain't it? And can you integrate this to finish the problem? Yes, you can. So then, yeah, so that's this guy. He's weird. All right, so I'm not really finishing him, but that's a good question. Any other good questions? Where are we? We did this problem? Oh yeah, we had to do integration by parts. Tabular method. We knocked it out. We're done. If someone had an initial condition, all it takes is some kind of initial condition here, and you got a little added work. You kind of wait till the end here, and you got a little added work. What would you do? Plug in a 0 for x, plug in a 3 for y, and try to find c. I think I'll just try that real quick. If this had an initial condition, then you plug in a 0 for x and a 3 for the y and a 0 for the x. You get 2 125ths plus e to the 0. E to the 0 is 1, so that is just a c. So what is c? C is
3 minus 2, 125th.
Yeah, 3 minus 2, 125ths, which everybody knows is 373, 125ths. Did I do that right? Might have done that right.
Yeah, that's right.
Thank God. All right. Yeah, just subtracted. I subtracted. Got a common denominator. Subtracted. Cool. There's my C. Anyway. All right. Well, all right, that's good. Listen, you guys can catch up to me in 2.3. Start working in 2.3. I want to mention a couple things before we quit here today. If I go back to 2.1, and I might not be able to finish this in 10 minutes, but in 2.1, there's two big things. There's two ideas. And again, we're going back to before you can solve DEs, okay? So some preliminary theory. And so we talk, there's this thing about slope fields. That's one concept that I'd like to discuss. And then there's a whole other concept. The book calls it a phase portrait analysis. And that's kind of fun, but it sounds wild, but anyway, there's these two ideas I want to discuss in 2.1, and I might not get to all of them. Check this out. This slope field idea is kind of wild. Look at this. This is a differential equation. You know? Pretend we don't know how to solve it. We actually got two methods to solve it now. We could probably do separate and integrate. We could probably do the integrating factor method. Would probably work. Either method might work on this one. But anyway, forget about solving it. To look at a slope field, here's what we do. We look at the XY plane, and when we're solving a DE, we're looking for the function y. We're looking for this function y, and what I have is dy dx. So what I have is sort of a formula. I don't have the function y, of course. That's what I'm looking for, I guess. But what I have is this dy. I have a little formula for his slope. I mean, that's the derivative is his slope, and so what I can do is I can like go around the xy plane at any point in the xy plane, like at the point 1, 1. At the point 1, 1, x is 1, y is 1. If I plug that in for the x and y variables, what would the slope be at the point 1, 1? The slope would be 1. And then what I do is I draw a little picture of a little slope of 1. I draw like a little line segment that has a slope of 1, which is that. Okay, guess what? I have to do that for every point in the plane. So this is not something you really want to do by hand, but you get the theory, maybe you get the idea, and you get the idea that the computer doing this for you would be pretty damn awesome. A little program that said, hey, draw these slopes all over the damn place. But what, let's just move over. If I was at the point 2, 1, is this 2, 1? If I was at the point 2, 1, what would the slope be? 2 times 1, the slope would be 2, so it'd be a little steeper. Or if I was at the point 2, 2, 2, 2 up here, the slope would be 4. Shit, that's pretty steep. What if I was at the point 0, 2 right here? 0, 2, 0, 2. The slope would be 0. I could draw a little line segment with a slope of 0. Now listen, I really don't want to sit here and do this by hand for all these points. So now I'm going to pretend, let's just pretend I did, and I get this kind of a picture. This is kind of what a slope field may look like, just a bunch of little line segments everywhere. And in our book, in section 2.1, our book has some pictures of slope fields. And if I put this on a quiz next week or a test next week, I'll give you a slope field. I'm not going to ask you to create a slope field. I'll give you a picture of a slope field. And then what we want to do is do this. This is the DE, and what we can do is we can not solve the DE, but we can speculate on what its answer looks like. If we have a picture of all the damn slopes, and if I tell you that I want to find the solution curve that goes through, watch this, that goes through, or the initial condition, y of 0 equals, hang on, y of -1 equals 2. So I'm asking to find a solution curve that goes through this point. I'll tell you what, let's find, where are you when you're on that point? When you're on that point, x is -1, y is 2. I've got to pay attention to the scale here, but I'd say that's -1 and that's 2. So I'm going through that point. So what I try to do is I start there and I try to do my best to work my way to the right and maybe to the left and do what the slopes tell me to do, and I try to draw a solution curve. That's what I'm really trying to do. Draw a solution curve.
At that exact point?
Well, that one point is the only point I know, and the rest is speculation based on what these little line segment slopes tell me to do. So if I start easing to the right, this is very crappy slope field. But if I start easing to the right, based on that, it looks like it's kind of going up a little. I'll just kind of go up a little. I mean, it'd be nice if somebody had some slopes right here and told me what to do. And I can sort of follow these slopes. Oh, okay, I'll go this way. Oh, it looks like, okay, I'll go this way. Oh, it looks like I need to get a little steeper here. And what if I went back to the left? Oh, okay, I'll try to follow these slopes. Look, I'll try to follow these slopes here. You see it? Anyway, it's interesting, and it's cool, and it's easy. You can take a look at the graph without ever solving the DE. It's kind of like I said, it's kind of a computer game, really. But we're going to do it by hand. I mean, that's all I want to say about slope fields. There's nothing to it. I'm going to give you a slope field. The book gives you a slope field, and you just pay attention to the initial condition and try your best to draw a curve through the slope field that follows the slopes. And yeah, that's it. So in 2.1, there's a little bit of homework where you could do that. There's pictures of slope fields in your book. I guess maybe you could draw in your book, or you could make a copy and draw on it. I don't know. Anyway, you could just practice with a pencil trying to draw through there. If I gave you a different initial condition, here, let me just try another one. Y of 2 equals 1. Where's that point? We already actually plotted that point. 2, 1, that was this point. So now if I head off to the right, you know, it looks pretty steep. I would be going pretty steep, but then it looks kind of like I should level off a little bit. This looks like I should have this slope. Looks like I don't know how good a job I'm doing. Remember, this was a crappy slope field. In fact, I don't even know what to do to the left. Look at this. There's a big gap. Nothingness over here, but yeah. All right, you guys, that's pretty easy. So you can try a few slope fields. Now there is one other cool idea in 2.1 that I'm going to quit today. I'm not going to get to that. But anyway, we'll get to that next week. Maybe I'll get into that Monday. This is in 2.1. This is sort of the second set of problems in 2.1. That's cool. That's interesting too. All right, so I'm done today. Hey, so you can do it. You guys can catch all the way up to me, except for this one little gap in 2.1 that I'm talking about. We've done a good job of covering this stuff. And I'll answer questions Monday and cover some other stuff Monday. To tell you the truth, the end of this chapter is a little anticlimactic. We skip 2.4. We do a cool idea in 2.5, a cool idea in 2.6. And we end up, and I think we're taking a test next Thursday, right? So we got a few days to get good at this. If we get bored before the test, I could ease on into chapter 3 a little bit before the test. But anyway, have a good weekend. Thank you for listening.